This story doesn't begin with a telescope. It doesn't begin with mathematics or genius or even curiosity. It begins with something far more profound, with perfect, terrifying silence. For 2,000 years, the stars gave us nothing. They hung in the night sky like fixed jewels on a black velvet dome, eternal and unchanging. They rose and set with clockwork precision, but they never spoke their secret. The one question every child asks when they first look up, how far away are they, had no answer. Not for the ancient Greeks with their brilliant geometry, not for the Arab astronomers with their exquisite catalogues, not for Galileo with his revolutionary telescope. The stars were silent, and that silence created a model of the universe so beautiful, so complete, that it felt like truth. It was the celestial sphere, a perfect crystalline shell surrounding our world, with every star embedded in it like diamonds in glass. This sphere rotated once a day, carrying the stars with it, the planets. They were different, wanderers who moved against this fixed backdrop, but the stars themselves, they were perfect, eternal, unchanging. I need you to understand something crucial here. This wasn't stupidity. This wasn't a failure of imagination. This was the only rational conclusion from the evidence available. If you measure something night after night, year after year, century after century, and it never changes, you conclude it's fixed. That's good science. But good science can be wrong. And what fascinates me isn't that they were wrong. What fascinates me is why they couldn't be right. What was missing? What invisible barrier stood between humanity and the truth of the stars? The answer is a whisper, a shift so small it's barely a suggestion, a measurement at the very edge of what humans can perceive. This is the story of breaking that 2,000-year silence. It's the story of the first person to hear the stars whisper their distance. And it's the story of how that whisper created a unit of measurement so strange, so counterintuitive, that it makes no sense to anyone outside a small community of specialists. This is the story of the parsec. And it begins with a problem so fundamental we've almost forgotten it was ever a problem. How do you measure something you can't touch? Imagine you're on a beach at night, looking at a ship on the horizon. You see its light. You know it's a ship, but how far away is it? If you're clever, you might use triangulation. You walk a measured distance along the beach. Notice how the ship appears to shift against the background and calculate the distance. Basic geometry. Now imagine the ship is so far away that walking any distance along the beach produces no visible shift at all. The ship appears fixed against the distant headlands. You could walk a mile, 10 miles, no change. What do you conclude? If you're ancient, you conclude the ship is infinitely far away, or at least so distant that measuring its distance is impossible. That was the stars. The beach is Earth. The walk is our orbit around the sun. The ship is any star. And for 2 millennia, no matter how far we walked from one side of our orbit to the other, the stars didn't appear to shift. The logical conclusion, they're infinitely distant, or at least too distant to measure. But here's where our story takes its first turn toward the strange. The ancient Greeks had a word for that fixed sphere of stars. They called it the firmament, from the Latin firmare, to make firm, to strengthen. This wasn't poetic language. They meant it literally. The stars were embedded in a solid, rotating sphere. Aristotle writing in the 4th century BCE, took it further. He argued the celestial sphere must be made of a fifth element, different from earth, water, air, and fire. He called it ether, or quintessence, literally fifth essence. This substance was perfect, unchanging, eternal. The stars partook of that perfection. Think about that for a moment. Not just wrong, but philosophically, metaphysically wrong. The stars weren't just far away. They were made of different stuff. They operated under different physical laws. This model persisted not because people were stubborn, but because every observation confirmed it. When the Greek astronomer Hipparchus compiled his star catalogue around 130 BCE, he recorded the positions of over 1,000 stars. 3 centuries later, Claudius Ptolemy created his even more comprehensive catalogue. The constellations hadn't changed shape. The stars kept perfect formation for 2,000 years. Every clear night provided evidence. The stars are fixed. The silence was absolute. I want to pause here and make you feel the weight of that silence, because we live in a different world. Now we know the distances to stars. We know their suns like our own. We know they're born, live, and die. The universe is dynamic, violent, changing. But for almost all of human history, the night sky was a clock, not a destination. It was a map for navigation, a calendar for planting, a backdrop for myths. But it wasn't a place you could go. The very idea was nonsense. What changed? 2 things, really. First, the Copernican revolution. When Nicolaus Copernicus proposed in 1543 that Earth orbits the Sun, not the other way around, he did more than rearrange the solar system. He gave us a moving platform. If Earth orbits the Sun, then in January we're on one side of the orbit, and in July we're on the opposite side. That's a baseline of about 300 million kilometers. Think about our beach analogy again. Instead of walking a few meters, we're now leaping 300 million kilometers. Surely that should make the nearby stars appear to shift against the more distant ones. Theoretically, yes. Actually measuring it, that was the second problem, because the shift is unimaginably small. Let me give you a sense of scale. Hold your arm straight out and look at your thumbnail. The width of your thumbnail covers about 1 degree of sky. Now, divide that degree into 60 equal parts. Each part is 1 arc minute. Now divide that arc minute into 60 more parts. Each of those is 1 arc second. 1 arc second is 1/3600th of a degree, to give you a physical sense. If you hold a tennis ball at a distance of 1 kilometer, the ball appears about 1 arc second wide. If you're standing on a beach watching a ship 10 kilometers away, a person standing on that ship's deck appears about 1 arc second tall. That's the kind of precision we're talking about. And the nearest stars, their parallax shift, that apparent motion caused by Earth's orbit, is smaller than 1 arc second, much smaller. 61 Cygni, the star that will become central to our story, has a parallax of about 0.3 arc seconds. That's like trying to measure the width of a tennis ball from 3 kilometers away with 17th century telescopes. Through Earth's turbulent atmosphere, it was considered impossible. And yet, the idea was too beautiful to abandon. If you could measure that tiny shift, you could use simple trigonometry to calculate the distance. Draw a triangle with Earth's orbit as the base. the star as the apex, measure the angle at the star. Basic geometry any student learns in school. The concept was simple. The execution was at the very edge of human capability. The first serious attempt came from an unlikely figure, Robert Hooke. Hooke is one of history's great polymaths, a man who contributed to optics, mechanics, astronomy, biology. He coined the word cell after looking at cork through a microscope. He formulated Hooke's law of elasticity. He was brilliant, ambitious, and in 1669 he decided to tackle the parallax problem. Hooke chose a bright star called Gamma Dra. He built a special telescope mounted in a tall building to minimize atmospheric distortion. The idea was clever. Mount the telescope high up above the turbulent air near the ground. He observed for months, took careful measurements, and detected what he thought was a shift in position. He published his findings. He claimed to have measured stellar parallax. At last, he was wrong. What Hooke had actually detected was something called stellar aberration, a completely different effect caused by the combination of light's finite speed and Earth's motion through space. Here's how aberration works. Light travels at about 300,000 kilometers per second. Earth orbits the Sun at about 30 kilometers per second. When you point a telescope at a star, you have to tilt it slightly in the direction of Earth's motion to compensate, like tilting your umbrella forward when running through rain. This causes all stars to shift slightly in the same direction. Hooke had discovered something real and important, just not parallax. This pattern, brilliant scientists finding real effects but misidentifying them, will become a theme. The signal was so buried in noise that even the best minds of the age couldn't extract it cleanly. William Herschel, the astronomer who discovered Uranus in 1781, tried a different approach. He reasoned that if you observe double stars, pairs that appear close together, one might be much nearer than its companion. The near star should show parallax, the far one wouldn't. He made thousands of painstaking measurements over years. He never found parallax, but his work wasn't wasted. He discovered that many double stars aren't just chance alignments. They're physically bound, orbiting each other gravitationally, binary star systems. This turned out to be one of astronomy's most important discoveries, giving us a way to measure stellar masses. Herschel's failed attempt to find parallax led to a discovery that transformed stellar astronomy. Failure, it seemed, could be productive. But it was still failure by the early 1800s. Measuring stellar parallax had become astronomy's great white whale. Everyone knew it should be possible, in principle, but nobody could actually do it. Some claimed success, but their results couldn't be replicated. The distances they calculated varied wildly. The problem wasn't lack of trying. The problem was that the measurement sat at the very boundary of what was physically possible with the technology of the time. The telescopes had mechanical wobbles larger than the signal, atmospheric turbulence, blurred images by several arcseconds, 10 times larger than the effect they were trying to measure. Temperature changes made telescope parts expand and contract. The astronomer's own heartbeat could introduce vibrations. Wind pushed on telescope tubes. Observatory foundations settled and shifted. The signal wasn't just buried in noise. It was buried under mountains of noise, and yet the prize was too great to abandon. If you could measure the distance to just one star, you would break the 2,000-year silence. You would prove the universe was measurable. You would give humanity its first real step into the cosmos. The question wasn't whether someone would succeed. The question was how, and the answer would come from a most unlikely person, a German accountant with no formal astronomical training, an obsession with error, and a patience that bordered on madness. Let me introduce you to Friedrich Wilhelm Bessel. Bessel was born in 1784 in Minden, Westphalia. He didn't start as an astronomer. He began his career as an accountant for a trading company. But in his spare time, he taught himself mathematics and astronomy. He was particularly interested in navigation, how to calculate positions using the stars. At age 20, Bessel calculated the orbit of Halley's Comet using old observations. He did this purely as a hobby, but his work was so good that a professional astronomer, Heinrich Olbers, noticed it and helped Bessel get a position as an assistant at an observatory. By age 26, Bessel was appointed director of a new observatory being built in Kingsburg. He would spend the rest of his career there, turning it into one of Europe's leading observatories through sheer force of meticulousness. Bessel became one of the most painstaking scientists of his generation. He was obsessed with precision and error analysis. This was still a time when many scientists took measurements somewhat casually, writing down whatever their instruments showed without carefully considering all the sources of error. Bessel was different. He didn't just take measurements. He analyzed every possible source of error. He built mathematical models to account for them. He repeated observations until he was absolutely certain of his results. He studied atmospheric refraction, how air bends light, and how that bending changes with temperature, pressure, and humidity. He measured how his telescope's metal parts expanded and contracted with temperature changes. He tracked mechanical play in his mount, wobbles in his building's foundation, even the effect of wind pressure on the observatory dome. Every possible source of error was studied, measured, and accounted for. This level of care was unusual for the time, and it's exactly what was needed to detect parallax in 1837. Bessel decided to tackle the parallax problem directly. He chose his target carefully, a star called 61 Cygni in the constellation Cygnus. The Swan. 61 Cygni wasn't particularly bright. You need a small telescope to see it clearly. Under dark skies, you might barely glimpse it with the naked eye. It's what astronomers call a fifth magnitude star, at the very limit of naked eye visibility. But 61 Cygni had one crucial property. It moved across the sky faster than almost any other star. This motion isn't parallax. It's called proper motion. The star's actual movement through space over time. Most stars have such small proper motions that they appear fixed even over human lifetimes. But a few nearby stars show measurable motion. Bessel reasoned that a star with high proper motion was probably relatively nearby. Think about watching cars from an overpass. The cars in the near lanes seem to zoom past, while distant cars barely seem to move. Same principle applies in space. 61 Cygni had one of the largest proper motions known at the time. Bessel guessed it was nearby, and therefore a good parallax target. From August 1837 through August 1838, Bessel made hundreds of observations. He used a specialized instrument called a heliometer. Is essentially a telescope with a split objective lens. The front lens is cut in half, and one half can be slid sideways relative to the other. This creates two images of whatever you're looking at. By adjusting how much you slide the lens, you can superimpose the two images or separate them by precise amounts. This design lets you measure tiny angles with remarkable precision. Bessel's heliometer could measure angles down to about 1/10 of an arcsecond. Under good conditions, cutting-edge precision for 1837. But Bessel didn't just point his telescope at 61 Cygni and measure its position. That wouldn't work, because he'd have no reference frame. The telescope itself might shift slightly. The building might settle. Instead, Bessel observed multiple reference stars in the same field of view. These were stars chosen to be so distant that their parallax would be essentially unmeasurable, effectively at infinite distance. Every clear night, weather permitting, Bessel measured the angular separation between 61 Cygni and these reference stars. He would measure the distance from 61 Cygni to reference star A, then to B, then to C, multiple measurements, multiple references, all to maximize accuracy and catch systematic errors. Over months, as Earth moved around its orbit, 61 Cygni traced out a tiny ellipse against the background of reference stars. In January, Earth was on one side of its orbit, and 61 Cygni appeared slightly shifted one way. In July, Earth was on the opposite side, and the shift reversed. The size of that ellipse directly gave the parallax, but extracting that signal required dealing with a host of complicating factors, each much larger than the effect Bessel was trying to measure. Atmospheric refraction bends starlight. The amount of bending changes with the star's altitude, air temperature, humidity, barometric pressure. A star near the horizon might appear displaced by half an arcminute or more, about 30 arcseconds, roughly 100 times larger than the parallax Bessel was measuring. He had to measure or calculate all these effects and subtract them out. The telescope's metal parts expanded when warm, contracted when cold. Even a change of a few degrees could shift the alignment by amounts larger than the parallax signal. The mount had mechanical play that changed depending on which direction the telescope pointed. Point east, gravity pulls one way. Point west, gravity pulls differently. Earth's axis precesses like a wobbling top, causing all stellar positions to drift slowly over time, a tiny effect over 1 year. But Bessel had to account for it. Then there's aberration, the effect Hooke had mistakenly identified as parallax. Aberration makes stars appear shifted by about 20 arcseconds, much larger than parallax. Bessel had to calculate and remove this from every measurement he observed at different times of night to see how changing altitude affected measurements. Higher in the sky, less atmosphere to look through, less refraction to account for. He recorded air temperature for every observation, barometric pressure, wind conditions. He measured the expansion and contraction of his telescope with thermometers attached to the metal tube. He developed mathematical formulas relating temperature to telescope length. He built models of mechanical flexure. Every error source got its own mathematical treatment only after accounting for everything else. After months of painstaking analysis, could he isolate the tiny parallax signal buried in the noise? His result, 0.3136 arcseconds. To appreciate how small this is, Imagine you're looking at a dime held at arm's length, about 60 centimeters away. The width of that dime, as seen from your eye, is an angle about 20,000 times larger than the parallax Bessel measured. He was measuring an angle approximately equal to the width of a human hair seen from 100 meters away, or the angle subtended by the period at the end of this sentence seen from across a football field. From this measurement, using basic trigonometry, Bessel calculated that 61 Cygni was about 10.3 light-years away. That's roughly 97 trillion kilometers. To put this in perspective, if you could somehow drive to 61 Cygni at highway speed to 100 kilometers per hour, the trip would take about 110 million years. Modern measurements give 11.4 light. Bessel was accurate to within about 10%. Extraordinary for 1838. Think about what this required. 13 months of nearly continuous observations. Bessel had to observe on every clear night, which in northern Germany meant dealing with clouds, rain, and short winter days, hundreds of individual measurements, months of mathematical analysis, calculations done entirely by hand using logarithm tables, no electronic calculators, no computers. The measurement was at the very edge of what was physically achievable with 1838 technology. But Bessel managed it through obsessive attention to detail, mathematical skill, and relentless patience. He published his results in late 1838. The silence was broken. Within months, the floodgates opened. Thomas Henderson, a Scottish astronomer working at the Royal Observatory in Cape Town, South Africa, published parallax measurements for Alpha Centauri. Interestingly, Henderson had actually made his observations before Bessel. Starting back in 1832, he had measured Alpha Centauri's position carefully over many months. But Henderson was cautious, perhaps too cautious. He saw a shift that looked like parallax, but he wasn't completely confident. He worried about systematic errors. He questioned whether his instruments were accurate enough, so he sat on his data, continuing to analyze it, hesitating to publish. When Bessel's announcement came in early 1839, Henderson realized his own measurements were valid and rushed to publish. His data was actually better than Bessel's. In some ways, Alpha Centauri is brighter and closer, making its parallax larger and easier to measure. Alpha Centauri turned out to be even closer than 61 Cygni, about 4.4 light-years. That is interesting. From a history of science perspective, Henderson actually made the first stellar parallax measurements. But Bessel gets credit for the discovery because Bessel published first. This happens sometimes in science. The person who publishes first gets the credit, even if someone else did the work earlier. It's why scientists often rush to publish as soon as they have solid results. Friedrich Georg Wilhelm von Stvar, working at the Dorpat Observatory in what's now Tartu, Estonia, measured Vega's parallax shortly after. Vega is much farther, about 25 light-years, making its parallax even tinier and harder to measure. Struve's measurement was less accurate, but still a genuine detection. Suddenly, after 2,000 years of complete mystery about stellar distances, we had distances to 3 stars, and more were coming. Astronomers worldwide began parallax programs. Within a few years, distances to dozens of stars had been measured. By the early 1900s, hundreds. By mid-century, thousands. Each measurement confirmed that stars were scattered at enormous distances far beyond anything in the solar system. Alpha Centauri, 40 trillion kilometers away, about 270,000 times farther than the Sun. Sirius, 81 trillion kilometers. More distant stars were even farther. This discovery fundamentally changed humanity's understanding of the universe's scale before parallax measurements. Some astronomers thought the Milky Way might be only a few thousand astronomical units across, perhaps 100 times the size of the solar system. After Bessel's work, it became clear the galaxy was millions of times larger. The Sun wasn't at the center of a small stellar system. It was one ordinary star among countless others, scattered across distances so vast they were hard to comprehend. Our sense of cosmic scale expanded enormously. The universe went from being a solar system plus a sphere of stars just beyond the planets to being a vast space containing objects at distances requiring trillions of kilometers to describe. This was as revolutionary as Copernicus discovering Earth orbits the Sun, or Galileo discovering Jupiter has moons. But as these measurements accumulated, astronomers faced a practical problem. How do you communicate these enormous distances? Writing out 97 trillion kilometers gets tedious quickly. Scientific papers were filled with huge numbers. Saying a star is at 657,000 astronomical units is awkward. Using multiples of the Sun's distance helped somewhat, but it still wasn't ideal. Someone, and history isn't entirely clear who first suggested it, proposed defining a new unit based directly on parallax geometry. The idea was beautifully simple and came naturally from the measurement technique itself. Take a right triangle. One side, the base, is 1 astronomical unit, the Earth-Sun distance. The angle opposite that base at the vertex where the star sits is 1 arcsecond. Now solve for the length of the long side, the hypotenuse, which is the distance to the star, using basic trigonometry, specifically the tangent function. This distance works out to approximately 206,265 astronomical units. In more familiar terms, that's about 30.9 trillion kilometers, or about 19.2 trillion miles. They called this distance the parsec, a contraction of parallax and arcsecond. The name itself tells you exactly how it's defined. Here's the crucial thing to understand. 1 arcsecond was chosen because it's a round number in the angular measurement system humans invented thousands of years ago. The Babylonians around 2000 BCE developed a basic number system. They divided circles into 360 degrees because 360 has many factors, divisible by 2, 3, 4, 5, 6, 8, 9, 10, 12, and more. This makes it easy to divide circles into halves, thirds, quarters. They divided degrees into 60 arcminutes because 60 is also highly divisible. And they divided arcminutes into 60 arcseconds for the same reason. This sexagesimal system, based on the number 60, is why we still measure time in 60-minute hours and 60-second minutes. The Babylonians invented it. The Greeks adopted it. It spread throughout the ancient world and persisted to today. But there's nothing physically special about this choice. It's pure mathematical convenience, based on ancient numbering preferences. An alien civilization using a different angular system might divide circles into some other number of degrees and define their angular units differently. The parsec is a consequence of human choices about how to measure angles, not anything fundamental about the universe. And virtually no star sits exactly 1 parsec from Earth. Our nearest stellar neighbor, Proxima Centauri, is about 1.302 parsecs away. The bright star Sirius is about 2.64 parsecs. Vega is about 7.7 parsecs. 61 Cygni is about 1.03 parsecs. The parsec doesn't mark any natural cosmic boundary. It's not the distance at which any particular physical process occurs. Stars don't start behaving differently at 1 parsec. There's no sphere of special significance at that distance. It's simply the distance that makes parallax arithmetic convenient, defined by an arbitrary angular choice. But that convenience turned out to be enormous for working astronomers, for astronomers doing parallax measurements every single day. The parsec had one massive advantage over any other distance unit. Measure a star's parallax in and its distance in parsecs is just 1 divided by that number. The relationship is direct and transparent. If a star shows a parallax of 0.5 arcsecons, it's 2 parsecs away. 0.25 arcsecons, 4 parsecs. 0.1 arcsecons, 10 parsecs. 0.05 arcsecons, 20 parsecs. Mental arithmetic. No calculator needed. No complex conversions. No looking up tables. Just invert the parallax, and you have the distance. When you're processing hundreds or thousands of measurements by hand, which is what astronomers did before computers, this directness is invaluable. Imagine you're working through a notebook full of parallax measurements. Star a 0.15 arcsecons gives 6.67 parsecs. Star B 0.28 arcsecons gives 3.57 parsecs. Star C 0.08 arcsecons gives 12.5 parsecs. You can do this math in your head while working through the observations. The relationship is transparent. If you measure a parallax of 0.05 arcsecons, you instantly know the distance is 20 parsecs. If you make a mistake somewhere and accidentally get 0.5 arcsecons instead, the distance comes out to 2 parsecs, and you immediately know something went wrong, because that would make the star one of the very nearest in the sky, which should have been obvious from its brightness and other properties. Using kilometers or miles would require multiplying by large conversion factors every single time. Using astronomical units would require dividing by 206,265 every time. Using light years would require multiplying by about 326 every time. Each calculation is an opportunity for arithmetic errors. The parsec eliminates that. By the late 1800s, astronomers had measured parallaxes for dozens of stars. Each measurement confirmed that stars were scattered at enormous distances. The parallax technique was working. Distances were being measured reliably. The parsec became the natural unit for expressing those distances. It wasn't an official decision by any committee or scientific organization. It happened organically because it was genuinely useful. Astronomers started using it in papers because it simplified their work. Other astronomers reading those papers adopted it because it made results easier to understand. Catalogs started listing distances in parsecs. Textbooks explained the concept. By 1900, it had become the default unit for stellar distances in professional astronomy. But something strange was happening, even as the parsec established itself. The unit was born from a practical need to simplify calculations for parallax measurements. But as astronomy advanced, parallax became just one method among many for measuring distances. New techniques emerged: spectroscopy, variable stars, supernova. Each new method reached farther into space than parallax could, and each new method had its own natural units, its own ways of thinking about distance. Yet the parsec persisted. It spread from parallax work to all of astronomy. Even when astronomers weren't measuring parallax at all, they reported distances in parsecs.y. Because once a standard exists, changing it is hard. Once enough people use a unit, it becomes the language of the field. Switching requires coordinated effort. It requires changing textbooks, retraining scientists, rewriting software once computers arrived, converting databases. The costs of change are high. The benefits are uncertain, so the parsec stuck. But as astronomy reached farther out to star clusters, to other galaxies, to the edge of the observable universe, a problem emerged. The parsec was too small. Writing 3,000 parsecs repeatedly was tedious. So astronomers borrowed the metric system's prefixes and invented the kiloparsec kpc-1000 parsecs. A typical globular cluster might be 15 kpc away. The center of our Milky Way galaxy is about 8.2 kpc from Earth. Then, in the 1920s, Edwin Hubble made one of astronomy's greatest discoveries. Those fuzzy spiral nebulae weren't gas clouds within our galaxy. They were separate galaxies, island universes containing billions of stars, located at staggering distances. Hubble measured the distance to the Andromeda galaxy, about 280 kiloparsecs. Modern measurements give 780 kiloparsecs. Writing that repeatedly was tedious. So astronomers invented the megaparsec MPC, 1 million parsecs. Andromeda is 0.78 MPC away. Other galaxies were even farther. The Virgo cluster, about 16 MPC. The Coma cluster, about 100 MPC. As observations pushed deeper, the gigaparsec GPC emerged, 1 billion parsecs. The edge of the observable universe is about 14 GPC away. We took a unit originally based on a convenient angular measurement for nearby stars and kept multiplying it by thousands because the universe kept getting bigger in our observations at each stage. The parsec stuck around simply because converting everything to a new unit would have been more work than just adding a prefix. The infrastructure was already built around parsecs. All the formulas, all the catalogs, all the mental habits of astronomers assumed parsecs. Switching would have required coordinated effort across the entire field for unclear benefit. This is where our first chapter ends, but not where the story ends. We've seen how the parsec was born from practical necessity. We've seen how it solved an immediate problem for astronomers measuring parallax. We've seen how it spread through the field organically. But something deeper is happening here. The parsec isn't just a unit, it's a fossil. It's a preserved moment from 1838, when Bessel first measured that tiny shift. It's a piece of history, embedded in the daily practice of modern astronomy, Every time an astronomer says megaparsec, they're invoking Bessel's meticulous work. They're standing on that foundation. And yet, the parsec creates problems. It creates a barrier between professional astronomers and everyone else. The public thinks in light years. Astronomers work in parsecs. This split means science communicators are constantly translating, and the public is constantly confused. It creates barriers between astronomy and other sciences. Physicists think in meters. Engineers think in kilometers. Computer algorithms expect standard units. Every interface requires conversion. Most fundamentally, the parsec is arbitrary. It's based on human choices, the Babylonian basic system, the division of circles into 360 degrees, the choice to use one arcsecon specifically. There's nothing physically special about one arcsecon. Nothing about the universe says this is a natural unit. An alien astronomer would be baffled by our parsec. They'd ask, why this arbitrary number? And we'd have to answer, because it was convenient for a measurement we made in 1838. That's not a satisfying answer. It's a historical accident, not a fundamental truth. Yet here we are, nearly 2 centuries later, still using it. Why? Because the weight of history is heavy. Because the infrastructure is massive. Because changing would be hard. But is that a good enough reason? As I look at the night sky now, knowing what I know about the parsec, I see something different. I see not just stars, but distances measured in this strange, arbitrary unit. I see the ghost of Bessel's careful work in every astronomy paper. I see the accumulated weight of nearly 2 centuries of practice. And I wonder, what if Bessel had chosen a different reference star? What if he'd measured a parallax of 0.5 arcsecons instead of 0.3136? Would our parsec be different? What if the Babylonians had used a based-in system instead of base 60? Would we even have arcsecons? Our science is shaped by these historical accidents. Our understanding of the universe is filtered through human choices made thousands of years ago. The parsec is a perfect example of this. It's a human construct imposed on the cosmos. It tells us as much about ourselves as it does about the stars. But here's the most fascinating question of all, the question that will drive our investigation through the coming chapters. If the parsec is so arbitrary, so historically contingent, so problematic, why does it work so well? Why has it persisted for nearly 2 centuries? Why does every professional astronomer still use it? Why have multiple attempts to replace it failed? There must be something deeper going on, something beyond mere convenience, something that makes the parsec not just a historical artifact, but a surprisingly robust tool for understanding the universe. What is that something? To find out, we need to look beyond Bessel. We need to follow the parsec as it travels from that first measurement to the heart of modern cosmology. We need to see how it became entangled with everything from the cosmic distance ladder to the expansion of the universe itself. We need to understand why. Sometimes the things that make no sense are the things that work best. But first, we need to understand the man who started it all. Not just Bessel the astronomer, but Bessel the obsessive, the perfectionist, the man who measured nothing for a year and found a universe. What kind of person does that? And what did it cost him? That's where our story turns next. If our most fundamental units of cosmic measurement are based on ancient human preferences rather than physical reality, what does that say about everything else we think we know about the universe? There is a particular kind of obsession that changes the world. It's not the flash of genius, not the sudden insight that arrives in a dream. It's slower, colder, more relentless. It's the obsession with error. Friedrich Wilhelm Bessel wasn't trying to discover a new universe. He wasn't dreaming of distant stars or cosmic scales. He was trying to measure one thing perfectly. And to do that, he had to measure everything else first. Every source of error, every wobble, every temperature fluctuation, every breath of wind. He wasn't just observing stars. He was auditing the universe. In the winter of 1837, in Kingsburg, a city on the frozen edge of the Baltic, C. Bessel began what looked like madness. Night after night, he measured the position of a faint, unremarkable star called 61 Cygni, and then he measured it again and again. He wasn't looking for movement, not yet. First, he had to establish what not moving looked like. He had to quantify stillness with such precision that any deviation from that stillness, any real motion of the star, would stand out like a single wrong note in a silent hall. This chapter isn't about discovery, not at first. It's about the preparation for discovery. It's about the thousands of hours of work that must happen before you can hear the universe whisper. Because here's the truth about Bessel's measurement. He wasn't measuring the star's parallax, not directly. He was measuring everything except the parallax, so that whatever remained, that tiny, stubborn residual that wouldn't go away, might be the signal. He was measuring nothing, deliberately, systematically, obsessively, and in that nothing, he would find everything. Imagine trying to hear a single drop of water fall in a thunderstorm. Not just any thunderstorm, a hurricane, with screaming winds, crashing waves, the rumble of the storm itself. That's what Bessel faced. The parallax signal he sought was the water drop. The hurricane was everything else: atmospheric refraction, bending starlight by arc minutes when he needed arcsecond precision, telescope metal expanding and contracting with temperature changes, the mechanical play in his mount's gears, the wobble of his observatory's foundation, the trembling from his own pulse, the aberration of light from Earth's motion, the precession of Earth's axis, the proper motion of the star itself, the gravitational pull of the moon, the distant tug of Jupiter. Each of these effects was larger, often 100 times larger than the parallax shift. Each would drown out the signal completely, if not accounted for. Bessel's genius wasn't in designing a better telescope. It wasn't in having sharper eyes. His genius was methodological. He decided to measure the hurricane. Every source of error would become a measurement in itself. Every confounding factor would be quantified, modeled, and subtracted. He wasn't just an astronomer. He was a forensic accountant of the cosmos, tracking every discrepancy, every anomaly, until only the truth remained. But to understand why this approach was revolutionary, why it succeeded where decades of brilliant astronomers had failed, we need to understand the world Bessel was working in. A world where good enough was usually good enough. A world where scientific instruments were trusted more than they deserved to be. Let me take you inside the Kingsburg Observatory on a typical night in December 1837. The cold is the first thing you'd notice. Not just winter cold, but Baltic winter cold, the kind that seeps through stone walls, that makes the metal of the telescope burn to the touch without gloves. The observatory, completed in 1813, was Bessel's kingdom. He had helped design it, overseen its construction, chosen every instrument. At the center of the main room stands the heliometer. It doesn't look like much to modern eyes. A brass tube about 20 centimeters in diameter, mounted on a complex equatorial stand, but look closer. The front lens is split in half. One half can be slid sideways by turning a micrometer screw. This is the key. The heliometer wasn't new. It had been invented decades earlier for observing the sun, hence heliometer, sun measurer. But Bessel had adapted it into something new, a machine for measuring the universe. Beside the telescope, on a small wooden table, are Bessel's notebooks. Not one, but several. One for raw measurements, one for temperature readings, one for barometric pressure, one for wind conditions, one for notes on seeing quality, the steadiness of the atmosphere. Bessel isn't just looking through the telescope and writing down numbers. He's conducting a symphony of measurements, each instrument playing its part. An assistant, often his dedicated collaborator, Johann von Magler, records readings as Bessel calls them out. Temperature at the objective, minus 4.2 degrees. Barometer, 758.3 millimeters. Wind, light from the northwest. Seeing, poor, tremulous, Bessel peers through the eyepiece. He's not looking at 61 Cygni yet. First, he's checking the reference stars, the distant, supposedly fixed stars he'll use as his background grid. He needs to confirm they're exactly where they should be. He's memorized their patterns, their relative positions. Any deviation means something's wrong. It takes 20 minutes just to prepare, adjusting the mount, checking alignments, letting his eyes adapt to the darkness, letting the telescope settle as temperatures equalize. Finally, he finds 61 Cygni. It's faint. To the naked eye, under perfect conditions, it's just visible as a smudge of light. Through the telescope, it's sharper, but still unimpressive. A yellowish point against black dot. Now the real work begins. Bessel turns the micrometer screw. The two halves of the objective lens slide relative to each other. In the eyepiece, two images of the star field appear. He adjusts until the image of 61 Cygni from the left lens superimposes exactly on the image of reference star A from the right lens. He reads the micrometer scale, 342.7 divisions. He records it, then he shifts again, superimposing 61 Cygni on reference star B. Another reading, 518.3 divisions. Reference star C, 276.1 divisions. He repeats the sequence, then repeats it again. 10 measurements of each pairing, 30 measurements total for this one observation. Each measurement takes concentration. The images dance in the eyepiece. Atmospheric turbulence makes them shimmer, blur, separate. Bessel waits for moments of stillness, when the air settles and the stars become sharp points. In those moments, he makes his readings. An hour passes. His eyes ache from squinting. His back aches from hunching over the eyepiece. The cold has numbed his fingers. He steps back. "We'll repeat in 2 hours," he tells his assistant. "The star will be higher, less atmosphere." They retire to a small side room where a stove offers meager warmth. Bessel doesn't rest. He begins calculating. He's not calculating parallax. Not yet. He's calculating corrections. First correction: atmospheric refraction. The air bends light. The amount of bending depends on the star's altitude, air temperature, pressure, and humidity. Bessel has tables he's compiled himself from years of observations. He consults them. Interpolates. Second correction: telescope flexure. As the telescope points at different altitudes, gravity pulls differently on the tube. It bends slightly. Bessel has measured this bend at every angle. He applies the correction. Third correction: thermal expansion. The brass tube expands when warmer, contracts when colder. Even a half-degree change matters at this precision. Thermometers attached to the tube give him the temperature. He has a formula. Expansion equals constant times temperature change. On and on. Aberration, precession, nutation. A smaller wobble of Earth's axis. Each has its formula, its table, its correction. By the time he's finished, the raw measurements have been transformed. The numbers on the page aren't what he read from the micrometer. They're what he would have read if there were no atmosphere, if the telescope were perfectly rigid, if Earth weren't moving, if ... if everything were perfect, except the one thing he's trying to measure. Only then does he look for patterns. Only then does he ask, has 61 Cygni moved relative to the reference stars? Not yet. One observation tells him nothing. He needs dozens, hundreds, spread over months. Only then will the pattern emerge, the tiny elliptical dance caused by Earth's orbit. Tonight's work, it's a single data point, meaningless, alone. Just one of hundreds he'll collect. This is the work, meticulous, repetitive, cold. This is what measuring nothing looks like. Now, let's step back from that frozen observatory and ask a fundamental question. Why was Bessel like this? Why this obsessive attention to error? Why this pathological need to account for every possible influence? To understand that we need to go further back, before Königsberg, before astronomy. Bessel was born in 1784 in Minden, a town in what was then Prussia. His father was a civil servant. The family wasn't poor, but they weren't wealthy either. Young Friedrich showed mathematical talent early, but there was no money for university. At 14, he was apprenticed to a mercantile firm in Bremen. He became an accountant. This is crucial. Bessel's first training wasn't in science. It was in bookkeeping, in tracking every penny, every transaction, every discrepancy, in balancing ledgers where the numbers had to match exactly while working. As an accountant, he taught himself mathematics and astronomy in his spare time. He was particularly fascinated by navigation, the problem of determining a ship's position from celestial observations. It was a perfect marriage of his accounting mindset and his astronomical interests. Navigation required precise measurements and careful error analysis. At 20, he took on a project that would change his life, calculating the orbit of Halley's. Comet Halley had predicted the comet's return in 1758. It had appeared on schedule, confirming Newtonian physics in a dramatic way, but its orbit wasn't perfectly known. Bessel decided to compute it more accurately using old observations. He did this as a hobby, nights and weekends, after his accounting work. He taught himself the necessary mathematics, calculus, perturbation theory. He sought out observations from old records. When he finished, he sent his work to the leading German astronomer of the day, Heinrich Olbers. Olbers was astonished. The work was professional quality, better than professional. It showed a mind uniquely suited to astronomy, patient, meticulous, mathematically gifted. Olbers helped Bessel get a position as an assistant at the Lilienthal Observatory near Bremen. At 22, Bessel left accounting for astronomy, but he brought the accountant with him. He brought the need for balanced ledgers, the suspicion of unaccounted for errors, the belief that if something didn't add up, you had to find why. This was unusual in early 19th century astronomy. Many astronomers were gentlemen scholars. They observed, they recorded, they published. They trusted their instruments. If two observations disagreed slightly, they might take an average and move on. Bessel didn't trust anything, not his instruments, not the atmosphere, not even himself. He believed every measurement was contaminated, and his job was to decontaminate it. Let me show you how radical this was with a specific example. The problem of personal equation. In the early 1800s, astronomers tracking the motions of planets or stars often used the Eye-and-Deer method for timing transits. They would watch through a telescope as a star crossed a wire in the eyepiece. They'd listen to a clock ticking seconds and try to note the exact moment of crossing. It was discovered that different astronomers had different personal equations, systematic delays in their reaction times. One astronomer might consistently record a transit 0.2 seconds earlier than another. Most astronomers acknowledged this as a curiosity. Some tried to correct for it, crudely. Bessel made it a science. He conducted experiments with his colleague, Wilhelm von Struve, the same Struve who would later measure Vega's parallax. They sat at transit instruments, timing artificial stars. They quantified their personal differences with precision. They showed how these differences changed with fatigue, with practice, with the brightness of the object. Then Bessel did something remarkable. He built the personal equation into his observational method. He didn't just note that he had a reaction delay. He measured it, modeled it, and corrected every observation for it. He was auditing his own nervous system. This mindset extended to everything. When he became director of the new Kingsburg Observatory in 1813, he didn't just install telescopes. He studied the building. He measured how the foundations settled over time. He tracked how different parts of the building expanded and contracted with temperature. He noted how wind pressure deformed the walls slightly. He didn't just accept these as unavoidable errors. He measured them so he could correct for them. He became famous for this. Other astronomers started sending him their problematic observations. Bessel, these measurements don't make sense. Can you find the error? He usually could. He had an almost supernatural ability to look at a set of numbers and sense where something was off, where an instrument had drifted, where an observer had made a systematic mistake, where atmospheric conditions had been misrecorded by the 1830s. Bessel was Europe's authority on astronomical precision. When he decided to tackle the parallax problem, it wasn't a sudden inspiration. It was the natural culmination of his life's work. He had spent decades perfecting the art of measuring tiny things. Now he would apply that art to the ultimate tiny thing. But there was another reason he chose 61 Cygni specifically. A reason that shows his methodological brilliance, even in target selection. 0.61 Cygni isn't bright. It isn't prominent. Most amateur astronomers today have never looked for it. But it has one extraordinary property. It moves, not its parallax motion. That's what Bessel was trying to measure. Its proper motion, its actual movement through space, relative to the Sun. 61. Cygni has one of the largest proper motions of any star visible from northern latitudes. It moves about 5.2 arcsecons per year across the sky. That doesn't sound like much, but in astronomical terms, it's sprinting. Bessel knew this. The star's large proper motion had been noted by the Italian astronomer Giuseppe Piazzi decades earlier. Piazzi had called it the flying star. Here was Bessel's reasoning. A star with large proper motion is likely nearby. Think about cars on a highway seen from an overpass. The nearby cars appear to zoom past. The distant ones appear almost stationary. Same with stars. If two stars are moving at the same actual speed through space, the nearer one will appear to move faster across our sky. So 61 Cygni was probably nearby, and nearby stars have larger, easier to measure. But there was a problem. The proper motion itself, 0.61 Cygni, isn't just sitting still, waiting for Earth's motion to make it appear to shift. It's moving on its own. And that motion is much larger than the parallax, signal. 5.2 arcsecon per year of proper motion. 0.3 arcsecons of parallax total, peak to peak. The proper motion is about 17 times larger. Over the 13 months of Bessel's campaign, 61 Cygni would move about 5.6 arcsecons on its own. The parallax ellipse is only about 0.3 arcsecons in size. Bessel had to separate these motions. He had to subtract the star's own journey from the apparent wobble caused by Earth's orbit. This required a breathtaking assumption that the star's proper motion was constant, that it moved in a straight line at constant speed. He had no way to know this for sure. Stars can accelerate, they can curve, but he had to assume linear, constant motion. Otherwise, the problem was unsolvable. So he built that assumption into his model. He treated the proper motion as a straight line, the parallax as an ellipse superimposed on that line, everything else, refraction, aberration, etc., as corrections. To both, mathematically, he was solving for multiple unknowns simultaneously: the star's starting position, the slope of the proper motion, line speed and direction, the size and orientation of the parallax ellipse, dozens of correction parameters. It was an inverse problem of staggering complexity, and he had to solve it with 1830s mathematics. No computers, no matrix algebra, just pen, paper, and logarithm tables. He used the method of least squares, a technique developed by Gauss and Legendre for solving exactly this kind of problem, finding the best fit to multiple observations with multiple unknowns. But here's where Bessel went beyond even Gauss. He didn't just apply least squares. He worried about the assumptions behind least squares. He worried about whether his errors were really normally distributed. He developed tests to check. He was auditing the statistical method itself, month after month. The observations accumulated. January 1838, Earth near one extreme of its orbit. 61 Cygni should show maximum parallax shift in one direction if it's nearby. Bessel measures, corrects, calculates. The numbers are messy. The residual, what's left after all corrections, is small, but is it real? Is it pattern or just noise? He doesn't trust it. Not yet. February. More observations. The star has moved from its January position, partly from proper motion, partly, maybe, from parallax. March, April. Earth moving around its orbit. If there's parallax, the apparent shift should change direction. Bessel's notebooks fill with numbers, columns of raw measurements, columns of corrections, columns of corrected measurements. He starts to see hints. After subtracting everything he can think of, 61 Cygni isn't quite where it should be if it were infinitely distant. It's off by tiny amounts, and those offsets seem to follow a pattern. They seem to trace ... an ellipse. Maybe, but maybe it's wishful thinking. The human brain excels at finding patterns in noise. Bessel knows this. He's wary of it. He introduces checks. He measures different reference stars. He observes at different times of night. He has his assistant make independent measurements. The hints persist. By June, Earth is near the opposite side of its orbit. If his January hint was real, the shift should now be in the opposite direction. He observes, corrects, calculates. Yes, the offset has changed direction. It's roughly opposite the January offset. His heart must have raced. After months of work, of cold nights, of squinting through the eyepiece, of endless calculations, he was seeing it. The signature of parallax. But Bessel doesn't celebrate. He doesn't announce. He doubles down. Because now comes the most dangerous part. Confirmation bias. Once you think you see a signal, every new observation tends to confirm it. You interpret ambiguities in favor of your hypothesis. You discount contradictory evidence. Bessel knew this danger intimately. He had seen other astronomers fall to it. Hooke with aberration, others with flawed parallax claims. So he fought against his own excitement. He looked for ways his conclusion could be wrong. What if his reference stars weren't infinitely distant? What if they had parallaxes of their own that would corrupt everything? He checked. The reference stars had small, proper motions, suggesting they were distant. But was that enough? What if his atmospheric refraction tables were wrong? He had compiled them himself from years of data. But maybe Kingsburg's atmosphere was different in some systematic way. What if there was an error in his heliometer, a systematic error in the micrometer screw? He tested it repeatedly, measured known angles, checked and rechecked. What if the star's proper motion wasn't constant? What if it accelerated? He had no way to test this directly. He had to assume constancy. It was his weakest assumption. He pressed on July, August, September. The ellipse should complete itself. The offsets should return toward their starting points. They did. By October 1838, Bessel had 13 months of data, hundreds of observations, thousands of corrections, pages upon pages of calculations. He sat down for the final reduction. This wasn't a single calculation. It was a campaign. He worked for weeks, isolating himself with his numbers, checking every step, repeating calculations, looking for inconsistencies. Finally, he had it. The parallax of 61 CYG.0.3136 ARCSECONDS with an estimated error of plus or minus 0.020 ARCSECONDS. TC calculated the distance, 10.3 light years, 97 trillion kilometers. He wrote it up, a meticulous paper detailing everything: his methods, his instruments, his corrections, his uncertainties. He sent it to the Astronomische Nachrichten, the leading astronomy journal. It was published in late 1838. The silence was broken. The reaction was immediate and profound. Astronomers across Europe read Bessel's paper with a mixture of awe and disbelief. The precision was unprecedented. The thoroughness was overwhelming. Every possible objection seemed anticipated and addressed. But was it real? The test would be replication. Could others measure 61 Cygni's parallax and get the same result? Thomas Henderson, at the Cape of Good Hope, had been observing Alpha Centauri. He had data showing a parallax, but he had hesitated to publish, worried about errors. When the paper arrived, Henderson re-examined his data. It held up. He published quickly. Friedrich von Struve had been observing Vega. He too had parallax measurements. He published within months. 3 stars had measured distances. The dam had burst, but something interesting happened in the aftermath. Scientists didn't just accept Bessel's number, they dissected his method. They realized that Bessel hadn't just measured a star's distance. He had created a new standard for how to do precision astronomy. His approach, measure and correct for every error. Source became the model. His techniques spread. His correction tables were adopted by other observatories. The heliometer, once a specialized instrument, became the tool of choice for precision astrometry. Other observatories built or acquired them. The method of least squares, previously used mainly by mathematicians, became standard in astronomical data reduction. Bessel had done more than measure a distance. He had changed how astronomy was done, but he paid a price. Let's talk about the cost of this kind of work. Bessel was 54 when he published the parallax result. He had spent more than a year in intense, focused labor. The observatory at King's was cold in winter, damp in summer. The work required staring through eyepieces for hours, often in awkward positions. The calculations strained his eyes. His health began to decline. He developed what was probably a form of arteriosclerosis. He had circulatory problems. He aged prematurely. But more than physical toll, there was psychological toll. The obsession with error isn't just a methodology. It's a mindset. It seeps into how you see the world. Bessel became known as a perfectionist, difficult to work with. He demanded the same meticulousness from his assistants that he demanded from himself. He was quick to find flaws in others' work. He published criticisms that were technically correct but often harsh. He had few close friends. His marriage was reportedly strained. His children found him distant. He had given himself completely to the work, and the work had taken him. A poignant story from later in his life. After the parallax success, he was celebrated across Europe. He received honors. Visitors came to Kingsburg to meet the man who had measured the stars. But Bessel seemed uninterested in the fame. He kept working. He turned to other problems, refining the constants of precession, studying the gravitational influences of planets, compiling ever more precise star catalogs. He was building a monument of precision, a systematic accounting of the heavens. In 1846, at age 62, he made a prediction that showed both his brilliance and the limits of his method. He had been studying the proper motions of Sirius and Procyon, 2 bright stars. Both showed wiggles in their motion, small deviations from straight lines. Bessel concluded these wiggles weren't random errors, they were systematic. He proposed that both stars had unseen companions, dark stars, orbiting them and causing gravitational tugs. It was a bold claim. Invisible stars, revealed only by their gravitational effects on visible ones. For Sirius, he was spectacularly right. In 1862, Alvin Graham Clark discovered Sirius B, a white dwarf companion. For Procyon, he was also right. Its companion was discovered in 1896. But here's the interesting part. Bessel made these discoveries using the same meticulous error analysis he had developed for parallax. He wasn't looking for new stars. He was trying to account for anomalies in the motions of known stars. He was auditing Sirius and Procyon, and the books didn't balance. The only explanation, unseen mass.